Okay, Unit 3, Section 3, zeros of a polynomial. We've got some definitions here. Pause if you don't know those definitions and read those. The first theorem is the fundamental theorem of algebra, probably pretty important. It says that every polynomial of degree 1 or more has at least one complex root. Very simple statement, very powerful statement. The number of zeros theorem, we'll just throw that in right now. Polynomial function of degree n has at most n distinct zeros. And then a corollary to that, we'll just toss this in, even though we're not going to graph in this section. But a degree n polynomial has at most n minus 1 turning points. The first thing we're going to do is learn synthetic division. So we have a polynomial divided by a binomial here. So 2x cubed minus x squared plus 5x minus 7 over x minus 3 to set this up. We take the number that makes the denominator equal to 0. We're going to put it in a box out front. We're going to write the coefficients in descending order. Then the first number comes straight down. Multiply the number out front by the number below the bar and put it under the next term. Then we add straight down. And once you've done that, you just repeat the algorithm. Now that's the side work. To write our answer, 53 is the remainder, 20 is the constant, 5 is the coefficient of x, and 2 is the coefficient of x squared. So the answer is 2x squared plus 5x plus 20, and then the remainder is written as the remainder value divided by what we were originally dividing by. Okay, the next thing that we got is the division algorithm, but in particular, let's take a look at the special case of the division algorithm that says if we want to factor out x minus k from the original function, it can be, the function itself can be written as x minus k times the quotient plus the remainder. So in this example 2, if we were going to factor out x plus 1, so if k is negative 1, then the factor is x plus 1. Then the first thing that we would do is do synthetic division. So we do our synthetic division again, and below the bar we get 5, negative 4, 5, and then negative 9 is the remainder. So what the special case of the division algorithm says is that the original function can be written as x plus 1, so x minus k, which is x plus 1, and then times the quotient, and then just minus 9 right there. That's the remainder. Okay, then the remainder theorem says for a polynomial function, if x minus k divides the polynomial f of x evenly, then the remainder r is f of that value k. And then the factor theorem, these kind of go hand in hand. If x minus k is a factor if and only if f of k equals 0. Ignore that. All right, so we're going to use the remainder theorem in synthetic division to find f of k, and k equals 2. So if k equals 2, that goes out front. Then we do synthetic division, and we get r equals 11. So what this says is the remainder is equal to f of k. So f of k equals the remainder. So in this case, f of 2 equals 11. And then I want to note that since f of 2 is not equal to 0, then x minus 2 is not a factor, and x equals 2 is not an x-intercept. So we'll just jot that down. And then also, let's make a note. Looking ahead to graphing polynomials, that f of 2 equals 11 means 2 comma 11 is on the graph. Okay, then we're going to kind of put it together a little bit. So synthetic division can be used to determine if x minus k is a factor of f of x, which in turn allows us to determine if x equals k is an x-intercept. So we're going to determine if x minus 2 is a factor of the function. In order to do that, we need to see if it divides evenly. So if x minus 2 is the factor, then k equals 2. Do the synthetic division, and then notice that we get r equals 0. So note that f of 2 equals r equals 0, and that means that 2, 0 is on the graph. So x equals 2 is an x-intercept, and then we can factor out the x minus k. So in this case, that'd be x minus 2, and then we'd have x squared minus 9. Then we can factor this using just normal factoring techniques. So x squared minus 9 factors into x plus 3 times x minus 3. So we can write that function into a product of linear factors. And if x minus 2 is the factor, then the intercept is 2, 0. If x plus 3 is the factor, then the intercept is negative 3. If x minus 3 is the factor, then the intercept is 3. Conjugate zeros theorem. So if we have a plus bi is a 0 of f of x, a minus bi also has to be a 0. So an example, 4 plus 5i is a 0, and we're asked to give one more 0 by the conjugate zeros theorem. 4 minus 5i also has to be a 0. The rational zeros theorem says any rational number roots of this polynomial come from factors of the constant divided by factors of the leading coefficient. So all we have to do is list out the factors of the constant, which would be plus or minus 1 and 3, the factors of the leading coefficient, which are plus or minus 1, 2, and 4, and then write all combinations. So 1 over 1, and then negative 1. 1/2, negative 1/2. 1/4, negative 1/4, and so on and so forth until you get the entire list. And so this is all possible rational number zeros of this function. Descartes' rule of signs says that if you count the sign changes in f of x, that can tell you the potential number of positive roots. So a sign change happens right here when we go from a positive coefficient to a negative, or vice versa. So here to here is not a sign change because both of those are positive. Here to here is not a sign change, both positive. Here to here is a sign change. So if one sign change tells us one positive root. So here's the key though. It's the number of sign changes between descending terms or less than that number by a positive even integer. So for example, real quick, if 6 sign changes in f of x, the possible number of positive zeros is 6, 4, 2, or 0. So it's not just equal to the amount of sign changes, it's that number or minus 2, minus 2, minus 2. Then for the negative sign changes, you calculate f of negative x. F of negative x changes the sign on all odd exponents. So 3x to the fourth won't have the sign will be the same because it's an even exponent, but the positive 4x would become a negative 4x. So here we only have one sign change in f of negative x, and that tells us it's the same statement but for the negative roots. So since there is one sign change in f of negative x, there is one negative root. Now there has to be 4 total roots, and if there's one positive, one negative, there have to be 2 non-real. And let's make another note. Non-real roots come in pairs. They always have to come in pairs. Okay, and then at the end of the notes, I just have compiled a list of all of the theorems.